let's imagine that we've got a wheel or something that is rotating, and let's imagine it starts off at, let's say, 2 revolutions per second, and it speeds up to, let's say, 5 revolutions per second, and let's imagine that this takes 10 seconds. So it's starting off slowly. So slowly at 2 revolutions per second, and then over the course of 10 seconds it speeds up, and after 10 seconds it's going at 5 revolutions per second. What is our average angular acceleration? Well, to put this in standard units to find out, what are the standard units of alpha? Well, standard units of alpha will be the units of omega, which are radians per second, divided by units of time, which are seconds. In other words, radians per second squared. So the units of alpha will be radians per second squared, very similar to the units of acceleration, which were meters per second squared. Okay, so to get these in standard units, we need to have omega in standard units. So we've got omega naught, which is 2 revolutions per second. In other words, 1 revolution is 2 pi, so this is 4 pi radians per second. The final angular velocity, omega, is 5 revolutions per second. 1 revolution is 2 pi radians, so 10 radians per second. Delta t will be 10 seconds. So what do we find for our average acceleration? It's going to be omega, delta omega, which will be omega minus omega naught, 10 radians per second minus, pi, lost a pi in there, 10 pi radians per second minus 4 pi radians per second divided by delta t, 10 seconds, and what do we end up with? We end up with alpha equals 1.88 radians per second squared. Radians per second divided by seconds, radians per second squared. Okay? Any questions? No questions? Okay, great, let's go. All right, so what have we done? Let's recap. We define the angular position, theta. From the angular position, theta, we define the angular velocity, omega. From the angular velocity, we defined angular acceleration. Well, this is exactly analogous to the way we defined the linear quantities. Theta was exactly the way we define position, x. Omega is analogous to the way we defined linear velocity v, and alpha is completely analogous to the way we define linear acceleration a. So what are the relationships between these 3 quantities, theta, omega, and alpha? Well, you shouldn't be surprised to guess that they're going to be exactly the same as the relationships that we have between x, v, and a. So while we had 4 kinematic equations for linear motion, we will have 4 kinematic equations for rotational motion, and they're going to look exactly like the linear motion equations with the replacement of theta for x, omega for v, and alpha for a. So we don't even have to derive them, we can just write them down, and here we have the 4 kinematic equations for rotational motion. Okay, so let's just write them down from what we already know. Okay, so the first one is what? Omega equals omega naught plus alpha t. So just like V equals V naught plus AT, omega equals omega naught plus alpha t. Next one was what? Theta equals 1/2 omega naught plus omega times t. So just like, oops, sorry. You didn't catch me on this one. Theta naught plus 1/2 omega naught plus omega times t. So we have to have that initial position in there. The next one is what? Theta equals theta naught plus omega naught t plus 1/2 alpha t squared, which is like x equals x naught plus v naught t plus 1/2 at squared. And the last one, omega squared equals omega naught squared plus 2 alpha theta minus theta naught. There we go. Let me make sure that I didn't make any mistakes here. I think that's right. Yep, looks good. Okay, so we can then solve these problems very much like we solved the problems with rotational motion, going through essentially the same process. So let me put up some a general outline of how we're going to solve these problems. All right, so for solving rotational problems, first thing, make a drawing. Now in this case, drawing might not be all that helpful because we don't have the kind of motions that we're talking about. Basically a drawing is just going to consist of something that's rotating. But it's important to show the direction. Typically, we will define motion that is counterclockwise as positive, motion that is clockwise as negative. And I'll come back to that. So just keep in mind, counterclockwise, positive, clockwise, negative. Then, define the orientation in your problem. How is this thing rotating? Third, look at the problem and think about what quantities do you have, what quantities don't you have, and what quantity or quantities do you want? What are you looking for? What is the question asking you for? Next, this is really important. Look at number 3 over again. Make sure that you have all the information possible. Sometimes some information might not be quite so obvious. If the problem states that an object starts rotating from rest, it doesn't actually give you the number 0, but you have to realize starting from rest means what? The initial velocity is 0. The initial angular velocity is 0. So make sure that you've got everything. Make sure you've got all that information. Finally, go to the equations and solve the equations. Solve for what you're looking for. If there's another part, maybe there's another part to the problem where it's asking you for something else, you might need to go back to 3 again, like we had in some translational problems. If it asks you for some different sort of situation, you might need to go back and do number 3 over again. But finally, think about your answer or your answers. Make sure that they make sense. Do they seem like they're reasonable answers? And always, as always, check your sig figs. Make sure that you're using the appropriate number of sig figs for the problem. Okay, so let's try a problem. We've got the equations. I'm going to erase these, but I'll put them back up as we need them. So let's imagine we've got a blender. So here's a blender. So here's the blade of the blender, let's say. So here's the blender, and it's rotating around. Let's imagine that the blender is rotating initially at 350 radians per second. So that's the initial, how it's spinning initially. Let's imagine that it rotates through an angle of 40 radians. While it does that, let's imagine that it is accelerating. It's speeding up with, it's speeding up at, let's say, 1,650 radians per second squared. And the question is, how fast is it rotating at the end of this motion? So, how do we proceed? Let's write down the variables like we did before. So, let's say before in terms of when we did the translational problem. Theta naught, theta, omega naught, omega, alpha, t. Now, typically for theta naught, you can choose your initial orientation any way you want, so it's essentially possible most of the time to always define, well, mostly always, to define theta naught as 0. So let's just imagine that our reference point is on our x-axis whenever the problem starts. So we can just set theta naught equal to 0. All right, so theta, do we know that? Well, we know that this thing rotates through 40 radians. So what is that? Well, that's got to be our final angle. If it rotates through 40 radians from an initial position of 0, we know that our final angle must be 40 radians. Omega naught, what is that? That's the initial angular velocity. Well, do we know that? Well, yeah, okay, that's exactly what the 350 is. So our initial angular velocity is 350 radians per second. Omega, our final angular velocity, do we know that? Well, no, we don't know that, but actually that's what we're looking for. The problem asked for what's the final rate of rotation? Well, that's what we know is the final angular velocity. So that's what we're looking for. Alpha, the angular acceleration, do we know that? Well, yeah, that's what the 1650 radians per second squared is. So we know alpha is 1650 radians per second squared. What about t? Do we know how long this takes? How much time is involved? Well, no, we weren't told anything about that, so we don't know t. Well, that's what we know. This is what we know. These are what we don't know. And this is what we want. This is what we're looking for. So, let's think back to the equations. Is there an equation that has what we're looking for in it, so an equation that's got an omega in it, where we know everything else? Well, if you think about it, the fact is, yeah, the fourth equation, that is exactly what that is. The fourth equation, omega squared equals omega naught squared plus 2 alpha theta minus theta naught. Okay, that's got an omega in it, so we could use that to solve for what we're looking for as long as we know everything else. Do we know everything else? Omega naught, yes. Alpha, yes. Theta naught, yes. So we could use that to solve for omega. So let's stick our numbers in. Omega naught is 350 radians per second squared plus 2 alpha 1650 radians per second squared times theta 40 radians minus theta naught, which is 0. And there we go. Multiply this out, add these together, take the square root. This is omega squared, so to find omega, we take the square root of that, and what we find is omega is equal to 504 radians per second. And there is our final answer. So, let's think about that. Does that seem reasonable? Well, we're starting off at 350 radians per second. We're speeding up at a pretty high rate for 40 radians. Well, 504. I guess it seems reasonable. At least it's not smaller than 350, which would not make sense. It's not some huge number like 10 to the 12th or something like that, which would really just seem outrageous. So it seems reasonable. And in terms of sig figs, if we look back at our numbers, check how many sig figs we're talking about here. There we go, 3 sig figs. So that looks pretty good. Okay. Now let's go back to the motion of our object again, some general object. There are a few other things that we can describe for this motion. So let's imagine we've got maybe a wheel or something, and let's stick a point on here. So there's our reference point. As this wheel is rotating, our reference point is moving around this circle, but at this particular instant, just like we talked about with uniform circular motion, that point is moving in that direction. So that's actually the velocity, the linear velocity that that point has. I'm going to refer to this as v sub t for the tangential velocity. The velocity vector is actually tangent to the circle, it's perpendicular to that radial line. As it's going around, you can just imagine at this particular point it's going that way along the circle, so the velocity vector is perpendicular to that radial line. It's tangent to the circle. Let's imagine that this is at some radius r, so our reference point is at a distance r from the axis of rotation. Now you can imagine that the faster the wheel is rotating, the larger the tangential velocity is going to be. If it's rotating slowly, v tangential is small. If it's rotating rapidly, v tangential is large. So the question I'd like to ask is, how is omega related to v sub t? How are those two things related to each other? Well, let's define a new quantity. Let's define the period. Period, capital T. Don't confuse this capital T for period with capital T for tangential velocity here. T here, like time, capital T is going to be the period of the motion. The period is the time for one complete revolution. In other words, how long does it take for this thing to make one complete circle, to go around in a circle? That amount of time is going to be one period. Now, we've got to be a little bit careful, because if omega is changing, then the period of the motion is actually changing. So let's just think about the period as the time that it would take for this thing to go around the circle if at that instant it were traveling, or it traveled at a constant uniform angular velocity for one complete circle. Does that make sense? So while omega could be changing as it's going around, slowing down or speeding up, the period of the motion would be changing as it's going around. If it's going very slowly, the period would be long. If it speeds up, the period would be shorter. So the period is actually something that can change with time along with the motion. Okay? So, what do we know? Okay, what I know is I just dropped my pen cap. Alright, so what is the tangential velocity in terms of the period? Well, we talked about this before when we were looking at uniform circular motion. If we think about a velocity, tangential velocity, as distance over time, for one complete circle, the distance traveled would be the circumference of the circle, 2 pi r. While that motion would take the amount of time for one complete circle, well, that's exactly how we just defined the period. So that would be over t. So the tangential velocity is going to be equal to 2 pi r over capital T, the period. Now, what about omega? Omega we know as delta theta over delta t. In other words, the angular displacement over time. Well, if we think about one complete circle, what's the angular displacement? One complete circle would be 2 pi radians. While the time for one complete circle, again, would be capital T. So we can actually rewrite these. We can say that capital T is equal to 2 pi r over the tangential velocity, while down here we could write that capital T is 2 pi radians over the angular velocity. And let's just equate these two things. They're both the period. Let's set them equal to each other. So we have 2 pi r over vt is equal to 2 pi radians over omega. Now, I'm going to do something a little bit funny here. I'm going to cheat just a little bit. These units, radians, that we're using to measure the angular position, they're kind of a very unique unit. They are basically kind of like a unitless unit. Sometimes in equations we want to put them in there. When we're emphasizing that we're talking about an angle or an angular velocity or an angular acceleration, we want them in there with our quantity, like 3 radians per second to emphasize that we're talking about an angular velocity in radians per second. However, I'm going to just take these out because they're kind of a unitless unit, and we're just going to keep in mind that omega is measured in radians per second, and okay, well that's it. We'll just take them out because we don't want them in there. So let's multiply these over. We're going to take omega over here, divide by 2 pi r, multiply by Vt, and what do we get? We have omega is equal to, actually I'm going to leave the r over here. So I'm going to multiply by omega, and I'll have r omega times 2 pi equals 2 pi Vt, and then we'll divide both sides by 2 pi. The 2 pi's cancel, and what do we get? Vt equals r omega. There we go. And there is a very simple relationship between the tangential velocity and the angular velocity. Vt equals r omega. And what do we have to do? We had to cheat a little bit. We had to drop that residual radian from in there. And it's because of the simplicity of this relationship and relationships like this that we actually use radians to measure our angle. If we used degrees, we'd have these extraneous factors of 360 divided by 2 pi or 180 divided by pi in there, and it's because of using radians that we'll end up with nice simple equations like this. Okay, now let's think about this. Let's rewrite this again.